Hello, my name is Owen Longcar, and I'm going to be teaching you the method of joints when solving just truss problems. So, the basic concepts. Now, trusses are just made up of two force members with these things called joints right here. Now, these joints, the force net, since we're taking a statics course, is going to be equal to 0. That means forces in equals forces out. So say we look at this one right here. If we draw a free body diagram of the joint at point C, we can see there's an outside force of P2 right here. And then there's these 4 beams right here. Now these 4 beams are going to provide a force on that joint. So they can either be in a thing called tension or compression, which those directions are not correct, but we'll get into tension and compression in just a second here. So basically, we have these 4 force members. So the free body diagram might look something like this, with this one pulling on it that way, this one pulling on it this way, this one pulling straight up, and this member might be coming in and pushing down to even everything out. So that's just an example. These might not be the correct directions of which way it will go, but these directions, the way we measure them is we call it either tension or compression. So like for this right here, say this member, it would be in tension if it was, the way I remember it is if it's pulling on the point. So that's a tension force. But then a compression force would be like this. Think of it as this member is compressing into the joint. It's not really. It's kind of confused me at first because I used to think tension like the beams being stretched, but that's not the case. Tension actually means the joint is being stretched. That's the way you have to think of it. And so initially I always got tension and compression screwed up, but you have to just remember, tension is when the joint is being pulled on, and compression is when the joint is being pushed on. And that was in reference to when you're coming from the side of the beam where it's on. If you would just say put the point here and the force this way for this beam, that would not be going into it. But tension and compression, just remember, draw your arrows within the beam, and if it's going out of the joint, that would be tension. If it's going into the joint, that would be compression. Okay? So that's tension and compression. Now, at anchoring points and reaction points, the method of joints is not necessarily, as cut and dry. So you wouldn't say like, oh, this force and this force have to equal 0. That's impossible, right? So because there's a reaction here. So the reaction can be, this way. It could be anything. So the method of joints really does not apply to that point. It's more of just joints that are free from outside anchoring points. Now, the real-world application of these trusses, they are very common, used to make bridges, like small ones like this. So you can see the same kind of idea we had was like right here. There's 5 2-force members coming in here, and there's some kind of force from the weight of the bridge that's being held up by this truss. And they could be very extreme, as in this example right here, where, this is a gigantic bridge that is built on the basis of trusses. And some kind of engineer would have had to calculate, for example, how this how much force would be on this member and whether the steel could hold it, something like that. That's what you could be doing in the real world with this skill. So like I said, sturdy bridges, cross gaps, and really any application you can think of to kind of use this. So like, obviously it's very common in bridges and very easy to think of things as a bridge, but like maybe a basketball hoop frame, is made up of these two force members. And that's really all it is. It's anything with a two force members and joints. So there's a lot of real world applications. Honestly, they're endless, and most likely in most engineering professions you're going to run into somewhere where you need method of joints. Now here's an example. So we want to find the force. Sorry, I gotta get my pen here. Got to find the force where of members CB, so this member here, and CD, and we're going to state whether they're in tension or compression. Now, all this is it's a very simple truss baseline problem anchored here. So it ends up we don't even have to look at this part, and we're going to state whether these are in tension or compression. So let's solve this problem. Okay, so we're looking for members CB and CD here. Okay, so we're going to first obviously draw our free body diagram. So our free body diagram at point C. Apologize for my handwriting. I'm not very used to getting on the mouse and drawing here. So basically, here's what we're going to do. We're going to have point C right here, okay? And we have going down, we have a 4,000 pound force going down. Then we have two forces coming in here. Let's just, you see, I'm just guessing right now which side, which way these will be going. Negative numbers will correct my guesses here. So this is AC and CE, all right? But we're just looking for these two values. So this is CD and this is CB. So we're just looking for these two values. And it turns out that since this is a symmetrical truss here, that if we split it down the middle and we look, we just think of symmetry here, that the force members on this side are going to be equal to the force members on this side, okay? So that means, in turn, CB equals CD. So, but we still have to find these two. So the way we find these is since the force net has to be equal to 0. So when we sum the forces of Y at this point, forces at Y, sorry about that, that's going to equal, so we're going to say up is Y positive, right? So we say since CB and CD are equal, we can say the vertical component of this force, this angle is 60, as shown in this. So we're going to say CB sine of 60 times 2, since we account for both of these, that's the force being pulled up. So that force minus 4,000 from this force right here is going to be equal to 0. So this is a very simple problem to solve. One variable, just solve for it. You get, we're going to add the 400 over, divide by 2. We get 2,000 over sine of 60 equals CB, which is actually equal, when you calculate it out, to 2,300 309.4. And then obviously, since CB is equal to that, this is also equal to CD because of the symmetry we discussed earlier. And then when we're looking for tension or compression, which is the last part of the problem, now since this value turned out positive, that means the way I drew it on my free body diagram is correct, okay? If this were to be a negative value, then I would just flip the way it's drawn in my free body diagram. So, like, for example, these two forces that I drew was just a total guess, and it could be flipped, and I would know once I calculated the rest of the method of joints. And if they were negative, I would flip them. But since this is a positive number, we do not have to flip these. So now, when thinking about whether this is in tension or compression, well, this is actually CB and CD are both pulling on the joint here. So since they're pulling on the board as we discussed earlier, that would be a member that is in tension. Tension, not compression. Compression is when it is pushing into the joint. The member itself is pushing into the joint. So since it's pulling on the joint, that would be tension. So CB, final answer here will be CB equals CD equals 2,309.4 pounds, and they are in tension. Awesome. So that's basically method of joints, and the problems will just get more and more intense as you go. Basically, all you need to know is sum of the forces in equals sum of the forces out, and then the tension and compression. It's a very simple concept to learn, and it just takes a lot of thinking to get through these problems. So don't get worried, you hang in there, and you'll get through it just like I did. Thanks for watching.